And this is how we do it. This is how we do it. We have the density of the fluid, it's the weight per unit volume, increasing linearly with depth. And this is shown in this little sketch here on the left. Let's get the mouse activated. Here's the mouse. Low at the surface and then increasing with depth. Okay, so now we have an object of a certain density, okay, that we give this object a certain density, and you can place it anywhere, okay, but it will have a certain equilibrium level, okay, where the ambient density of the fluid is the same as that of the object. What it means is, if you place your object directly at that equilibrium level, your object will not move at all. There is zero buoyancy force. But what happens if you place your object somewhere else? So what can you do? You can work out what is the density change with depth. Okay, and this is the little formula that you can. This rho 0 is a constant reference value. This is actually the density at the surface. Okay. And then you have it increasing, okay, with depth. This is the magnitude of the vertical coordinate. Okay? This is the distance from the sea surface. And then you have the degree. This tells you how much it does change per meter depth change. Okay, it has the n square in it and the g. So with this formula, you can prescribe the initial vertical density stratification, but you can also tell at any level, vertical level, what the density is in the fluid. Yes, this one is actually a function. You plug in a value of z and it returns you a value of the ambient density. Okay, and the n square is, we had that before, and these values are prescribed. Indeed, in Fortran, you can't write n to the power of 2. You might have to write just n2 for this parameter. Okay, g you have to prescribe in rho 0 too. All right, so let's continue.